and dynamic manipulation of deformable objects. Please go ahead.
All right. Thanks, Dimitri, for the introduction. I'm Cheng. I'm a second-year PhD student from right here in Columbia. And today I'll present Iterative Residual Policy, a joint work with Toyota Research Institute. We are interested in the task of goal-conditioned dynamic manipulation of deformable objects. For example, hitting a target accurately with an unknown rope, or placing a tablecloth to a precise location. To the best of our knowledge, no existing robotic systems can solve this task. Why is it so hard? Well, under dynamic actions, we can no longer ignore the object's physics during planning. Yet, the physics of deformable objects are notoriously difficult to model. And even if we have a perfect model, we all know how hard it is to tune the simulation parameters for even just one object. And to make things worse, our tasks require high precision to achieve the goal, with a tolerance of a few centimeters. And to be honest, the whipping task in particular was quite hard even for me. Given an unknown rope, it's close to impossible for me to hit the goal in my first attempt. But the good thing is that after each attempt, I can get closer and closer and eventually hit the goal. So what did I learn during this process? Was I able to learn the mapping from action to a full trajectory? I don't think I can. Was I decoding some key rope parameters, like the length or density? I don't think I can either. Did I bump into the goal via some random acceleration? Unlikely, given the size of action space and the tight tolerance required. However, these are the popular methods that we use today to solve similar problems. So if that's not what we learned, then what is it? I think I have this intuition about how adjusting the action will affect the trajectory. For example, swinging harder will make the rope reach higher, and extending my arm will make the tip go further. It's hard to know how exactly the trajectory will change based on my action, but my guess for which direction to change my action is almost always correct. And therefore, our hypothesis is the knowledge about this change or adjustment is much easier to learn and generalizable to different objects. And therefore, in this work, we formalize this intuition into an algorithm called Iterative Residual Policy. And here's how it works. At its core, the algorithm learns a delta dynamics model that takes in the observed trajectory and a delta action as input, and predicts the updated trajectory with the delta action applied. Here, we parameterize the action with two target joint angles and a maximum joint speed. The trajectory is represented as the occupancy grid. By sampling different delta actions and predict the corresponding trajectory, our algorithm is able to iteratively select a better action and get closer and closer to the goal. Note that this delta dynamics model is trained entirely in simulation. And what does a simulation look like? On the left is a tip trajectory of a simulation system we set up with measured parameters. And on the right is what it's trying to match on real world. And as you can see here, we have a huge sim-to-real gap. Our hope is that learned delta dynamics model can lead us toward the correct general direction, and the simulation don't have to be very accurate. And here is the system in action. We track the tip of the rope with a camera and use the trajectory as input. The error is defined by the shortest distance along the trajectory to the goal. And then the algorithm will sample a set of delta actions from a Gaussian distribution, and the width of this Gaussian distribution is scaled proportionally with the error. And then we predict the trajectory for each delta action, and the delta action associated with the smallest error is selected for next step execution. This process will repeat until convergence, and it usually takes in less than 10 steps for this task. All right, that's for one rope. And in the following experiments, we want to systematically test our algorithm's generalization capability against different ropes with significantly different physical parameters. And in all following experiments, we use exactly the same model trained in simulation only. And here, I want to show you how big is the difference between different real-world ropes. And what you see here are the tip trajectory of different ropes executed using exactly the same robot action. And as you can see, they're very different. The second one on the left is not even a rope. It's a long piece of cloth that has much higher air resistance compared to a rope. The third one is a bullwhip, which is quite stiff and has non-uniform linear density. The effect of these properties are not captured at all in our training data, which collected in simulation. And therefore, it really requires a system to adjust using visual feedback to accommodate these different novel rope dynamics. And here is the resulting trajectory of the policy after policy converges on each goal. And as you can see, the policy will choose different actions to reach the same goal to accommodate different rope dynamics. The accuracy here is very close to the limit of our trajectory representation resolution. And we also want to highlight our sample efficiency here, since all of these results converges in less than 10 steps in real. Next, we want to show a less common form of generalization, which is against different robot hardware embodiments. We vary the length of the robot's last link, which changes the mapping between action parameters and their effect. And again, exactly the same model trained in simulation is used. And as we can expect, robot systems with different robot hardware embodiment comparing to the training setup started out with a much higher error. But regardless, it's able to adjust using visual feedback and get good performance. And here's the numbers we get in real. The left column stands for optimal action in simulation, which is a very strong baseline. We basically manually measure the parameters of each rope, manually model them in Mujoko simulation, and then brute force optimize the action for each individual rope in the simulation. And therefore, it represents an upper bound for analytical model-based controls performance in our simulator for this task. However, as you can see, it still results in more than 10 centimeters of error in real. In comparison, our method achieved an error that's an order of magnitude lower. And then we want to further stress test our system's robustness against unexpected changes. We first let the system converge on a given rope and goal. And then I come in and tie several knots on the rope, which changes linear density and length. And as we can expect, it immediately results in much higher error. But regardless, the system can adjust using visual feedback and quickly regain good performance. This actually happens to us multiple times organically during our experiment, because sometimes the rope just ties knots on itself. But regardless, the system still works, and then we only see a spike in loss. Finally, we want to demonstrate the generality of IRP framework by applying it on a slightly different task, which is cloth placement. The task is to place tablecloths for a precise location given a target pose, where the pose is defined by 9 key point locations on the cloth. Note that some of these target poses are outside the robot's physical reach range. Therefore, dynamic actions is required to solve this problem. And here are 2 typical strategies learned by our algorithm. In the first case, the cloth landed a bit too close compared to the goal. And in the second case, the cloth folded by itself due to high density. Based on this observation, the algorithm will increase stroke to swing further in the first case, and decrease speed to prevent folding in the second case. Our algorithm will continue to adjust action until convergence, which usually takes 3 steps for this task. And OK, here's our takeaways. Even though we've only tested on 2 tasks, we believe the formulation of iterative residual policy is quite general and is applicable to many tasks with complex dynamics. As long as, number 1, your state is resettable after a failed attempt, and number 2, your observations are trackable. For example, in our case, the goal and the tip location can be tracked as key point throughout the execution. What we learned from this project is that for some cases, instead of learning the full dynamics model, which maps from action to their effect, learning changes in action to changes in their trajectory is much easier to learn and generalizable to different objects. Because the direction of this change is invariant against many physical parameters that we have tested. We also want to say that IRP is a new way to distill relevant knowledges from existing simulators, especially when they're inaccurate. If we think about our existing simulators, a lot of them started out with gaming application in mind, and therefore they trade accuracy for speed. But still, our human can transfer our real-world skills to these games just fine, which means that the simulator must be doing something right. And our goal should be, we should figure out the right way to use these simulators to unleash their full potential in robotics. Thank you. That's it for my talk, and you can check out our code and data in this URL, and I'm happy to take questions.
Hello. Thank you very much, Cheng. Let's open it up for questions. Do we have any questions from in the hall? Yeah, go ahead.
All right, thank you. Very cool work. Thanks a lot for the presentation. I'm wondering, in the rope task, have you tried to use multiple key points on the rope instead of just one key point at the end of the rope? And if so, does that improve the performance?
So in our case, we don't think that's necessary, so I haven't tried. But if your goal is to hit, for example, multiple points in particular as a goal, I think that's definitely something that will be necessary.
Yeah, I'm asking this because I think maybe having multiple key points on the rope will help the model to better understand how the change of action will affect its trajectory.
Okay.
Yeah, but anyway.
I think that's possible, but in our case, basically we're abstracting away the complex dynamics throughout the entire rope, and we're only summarizing them as a trajectory of the endpoint, and which also contains a lot of information on its own. At least for our task, we believe that's quite necessary.
I see. Thank you.
Thank you.
Thanks for the talk. So you guys tested on both like 1D and 2D deformable objects. Do you guys have any future plans on like perhaps like a 3D deformable objects?
I think it will be challenging because one limitation in our case is that the key states need to be observable. I think it's possible given a complex shape. We only track if you only care about things on the surface. But if some complex deformation is happening inside the 3D object, then it will be kind of challenging to apply this method directly.
Thank you.
Thank you.
Really good work, thanks. So as far as the motivation goes, I mean, if you think at how humans do it, we also don't track accurately the tip of the rope. So do you think this work can be modified to use just binary feedback, success, failure, and modify the actions from that? Yeah,
I have to think about this. I think given only binary feedback is possible, but given a scalar feedback, I think it's potentially possible. Let we know the direction, the distance to the goal, and we can potentially infer kind of like a Jacobian to which where to adjust.
I had a question about the delta dynamics. So it seems like there's a forward dynamics where a change in action maps to a change in trajectory. But when you're updating in your iterations, you would need the inverse.
Sorry, can you repeat your last sentence?
But when you go from iteration to iteration, you need some sort of an inverse, right? Where there's a desired change in trajectory. How do you compute a desired delta action?
No, so actually the model takes in delta action as input. So what we did is that the model gives in the current observed trajectory from the last iteration, and then it apply a delta action on it, and it outputs what it's going to be like after delta action has been applied. So what it is kind of like a random optimization. So we basically sample a bunch of Gaussian delta actions from a Gaussian distribution, and then we feed all of them through the network and find which trajectory is closest to the goal.
Okay, thank you.
Thank you. Please.
Yeah, very great work. So I noticed that all your actions is kind of open loop. Do you have any intuition like how this idea can be applied to closed loop actions where you need to adjust the action at every time step?
First, we believe our method is closed loop, okay. Although it's closed loop between trajectories.
Yeah.
However, if you want to do to me, because imagine even if you send a wave through the rope, it still takes some time for it to propagate to the tip. Given the speed of our action, I think it's quite difficult to affect the tip precisely. During the execution, because the wave propagation might not even reach the tip yet in that case.
I say thanks.
Great question. Thank you.
Okay, I had a quick question just to wrap it up. Have you explored different kinds of action representations that might be more descriptive of the tasks you want to do, or are these actions represented at a very low level, like joint torque commands, things like that? Yeah, so in theory, the framework of iterative residual policy should be agnostic to these specific details about action representation. But so we settled on this case. Actually, in the beginning, we tried trajectory optimization style representation, where we basically repeated the action as a variable throughout time. But we realized that that's too much degree of freedom. And then we were inspired by a work from Northeastern University, and where they basically study biological stuff on how they manipulate. And they use a minimum jerk action primitive
which they found is what the human uses for this task. And we basically slightly modify it to use like trapezoidal sweep profile, which is easiest to map to a robot action space. But I do think if we want to scale it up to much higher dimensionality for action primitives, we probably need to replace the random optimization part with some kind of like, for example, long-driven dynamics or something like that to do a gradient descent to solve the dimensionality problem.
Great. Okay, let's thank our speaker again.
Thank you.
Okay. Okay, so next up we have Benjamin Eisner presenting Flowbot 3D, learning 3D articulation flow to manipulate articulated objects.
Great. Hey everybody, my name is Ben, and I'm presenting some work on manipulating articulated objects conducted by me, Harry Jang, and David Held at Carnegie Mellon. Articulated objects are everywhere. We interact with them all the time. We open doors, drawers, laptops, staplers, refrigerators, all these things without even thinking about it. We can estimate how objects can move just by looking at them as well. Even though you may not have seen these specific objects before, you've likely seen similar objects, and therefore you can imagine how they might move and how you might use them. And in fact, you definitely can. We want robots to have the same estimation ability. So how might we construct a robot learning system to successfully manipulate articulated objects just from raw visual observations? Well, one common paradigm in robot learning is to learn a big end-to-end neural network model, which maps directly from raw observations to low-level robot actions. This style of approach can be quite powerful because it can directly optimize for the manipulation task at hand. However, it's often quite hard for these end-to-end models to generalize well outside of their training domain. Now, at the other end of the spectrum, you can design a modular visual scene understanding pipeline which is tailored to the task of articulating objects. This might consist of, say, a segmentation model which segments discrete objects in the scene and then further segments out each part of each object. Then you might want to determine which of those parts are connected to each other and build some kind of kinematic tree connecting all the parts that you found in each object. And then for each of the articulations you find, you might want to estimate the exact screw parameters which govern the articulation. And then once you've parsed this whole representation, you can pass this to a motion planner, which can grab the part you want to move and use the estimated structure of the object to devise a good path to articulate the part. So when this is designed correctly, such modular approaches can generalize quite well, better than end-to-end approaches, particularly when it's difficult to collect many real-world trials. Now, there are points of failure in the system. There are many of them. Each of these estimation submodules is kind of an open area of research in itself, and an error in any one module can derail the execution of the system. So this can be quite brittle. We'd like an approach that gets the best of both worlds, allowing us to impose some domain knowledge into the system while having fewer points of failure. So one way we could do this is with estimating visual affordances and motion planning directly on top of these affordances. This style has fewer points of failure and optimizes an objective closer to the end task while providing better generalization properties than a full end-to-end method. However, this means we have to choose the right kind of affordance to estimate for the system to work. So, okay, let's think about this from a physics first principles perspective. The two most common types of articulations are sliding prismatic joints and hinged revolute joints. Okay, we'll look at prismatic joints first. Let's say each drawer in a chest, each one of these drawers is a prismatic joint. Each of these drawers has 1 degree of freedom along the axis V in the diagram. And the most efficient policy to actuate this articulation is to apply force directly to the surface of the object parallel to the axis V. Now for revolute joints, such as the doors on this cabinet, the most efficient direction to apply force is perpendicular to both the axis of rotation and the radius connecting the contact point to the axis of rotation. Now you get the most leverage by choosing a contact point that is far away from the axis of rotation, so that means you need to apply less force to generate the same torque. So to articulate both prismatic and revolute objects, we'd like an affordance that tells us which direction we should apply at every point should we apply force at every point, and at which points in the object give us the most leverage to articulate that part. With these goals in mind, we present our chosen representation for affordances, which is 3D articulation flow. We assign a 3D vector to every point on the object. The direction of this vector describes how that point can move under instantaneous articulation, and therefore which direction of optimal force is at that point. The magnitude of the vector describes the relative leverage at that point. So, all that you need to do is to look at this diagram here. You see these red vectors, which are the 3D articulation flow. The longer vectors occur further from the door hinge, and they all point in the direction that the door will move as it swings out. So given this representation, all the robot needs to do is grasp a high leverage point on the object and articulate the object in the direction that that flow points. Okay, so how do we go about predicting 3D articulation flow? Well, we take a point cloud observation, we run it through a standard PointNet++ backbone, and output our estimate of 3D articulation flow. Specifically, for each point in the input, we predict a flow vector, delta x, y, and z, which indicates the amount that that point would move if a small articulation were to be applied at the opening direction. Now, we can compare this predicted articulation flow directly to some ground truth articulation flow, which is computed from the known kinematic structure of the training objects that we have in our data set. And we can supervise this articulation flow with the mean squared error loss between the predictions and the ground truth. Now we'll describe how we can use this 3D articulation flow in a real robot system, which we call Flowbot 3D. First, we use a depth camera or LiDAR to get a partial point cloud observation of the object, and then we use our 3D articulation flow estimation module to densely predict the 3D articulation flow at every point in the input. Then we execute a two-phase policy. First, we select a contact point on the object, which amounts to choosing the point with the highest leverage subject to the constraint that the point is graspable. So for a suction gripper, we only choose points with low estimated surface curvature, and this is a simple heuristic that works pretty well. We can then use a motion planner to send the robot to that grasp location and execute the grasp. Once the robot has grasped the object, we can directly take the 3D articulation flow we just predicted at that contact point and set that as the desired direction to move the gripper. Then we can use motion planning to move the gripper the direction a small amount. And finally, we can close the loop by taking another point cloud, getting the articulation flow, executing a small motion, and repeating. We repeat until the object has been fully articulated. So the only learned part of this system is that articulation flow estimation module. To train this, we select objects from the PartNet mobility dataset and train a single model across examples from 11 different training categories. We use a simulator to get the ground truth articulation flow from these categories. We can then test on 10 unseen categories of objects, as well as a real-world collection of articulated objects that we've found in the real world. For our real-world physical setup, we can use a robot arm with a suction gripper and the object in a workplace. Object in the workplace with a fixed depth camera pointed at the scene. Now we'll talk a little bit about how the system performs on both real and simulated tasks. You can see some example success cases here. Let's take a look at some quantitative results, where we're seeing how often a policy will open an object. First, we compare against an end-to-end method, which directly outputs low-level robot actions. We see that even for the training objects, when viewed in unseen poses, the end-to-end method performs very poorly on this task. The y-axis here is the success rate, meaning how often the policy successfully opened the object more than 90% through its range of motion. Next, we compare directly against regressing articulation parameters, as well as a sampling-based direction scoring module, similar to the network proposed in UMPnet. Our method significantly outperforms these prior approaches, succeeding 3/4 of the time. This relative success holds for entirely unseen test categories of objects in simulation, and even on real-world objects. So, in essence, our system generalizes to both unseen objects and to real-world objects. To give you a sense of what predicted articulation flow looks like, here are some examples. In both cases, the network learns to predict very consistent flow, and it predicts flow only on the parts of the object which can move. On the test object, when the points are moving on the moving part become a little occluded, the prediction quality degrades a little bit, but the majority of frames and views give a reasonably accurate estimate. So, why does this system transfer well to the real world with a minimal drop in performance? We think that this is because of two reasons. First, the input data is a point cloud, which looks relatively similar between simulation and the real world. And second, we're really learning a dense object-centric representation, which is a function of the kinematic properties of the object instead of learning dynamics or any other kind of property, which is difficult and notoriously difficult to transfer from sim to real. All right, let's take a look at some real-world results. We compare our method with an end-to-end policy in the real world. As we can see, Flowbot 3D is able to repeatedly choose a good direction in which to open each object, while the end-to-end method is not consistently able to do so. Now, these jars aren't technically articulated, but we treat jar lids as if they were prismatic joints. This follows the convention from the Sapien dataset. Now, when the objects are very heavy or fixed to the table, Flowbot 3D still succeeds with a small amount of compliance in the gripper and controller, making their policy robust to small prediction errors. And here's my favorite example, which is lifting a toilet seat. All right, to recap. Flowbot 3D estimates 3D articulation flow and uses motion planning to articulate novel objects. It significantly outperforms end-to-end policies while avoiding the brittleness of modular approaches. And best of all, we generalize to unseen objects and transfer to the real world without retraining. Thanks, and I'll take questions now.
Thank you. All right, questions?
Okay, I'll go first. Thanks a lot for the talk. I really like this work. A couple questions. So one, you motivated in the context of objects with multiple parts, but it looked like this method only applies to objects with 1 degree of freedom. Is that correct? And if so, how would you extend it? And then two, I guess maybe pertinent to the sim to real, it looked like the objects were segmented from clutter and everything else around them. Is that the case, or am I misunderstanding?
Yeah, so for the first question, it's about multiple articulations. So the nice thing about the dense representation is that if the object has multiple single degree of freedom articulations, like a set of shelves, all of them will get the same flow, or not this exact same flow, but they'll all be treated independently because it's a dense prediction. However, if the links are kind of connected in a kinematic chain, we didn't really test on those kinds of examples. You could imagine the flow still does work, like there is an instantaneous displacement that does happen, but it might be a little more difficult to generalize and predict without a more robust representation of that chain itself. And the other one was, sorry, what was the second part of the question?
I think it was, pertinent to the sim to real, it looked like the object was, the point clouds are nice for transferring from sim to real, but the objects looked like they were clearly segmented from any clutter or background.
Yeah, so in that case, we did segment it from the background. Really, in the real world, it was just plain subtraction. We didn't really worry about training robust to a bunch of visual noise.
Cool, thanks a lot, I like the work, thanks.
Yeah, thanks.
I had a very similar question. So you also subtracted the robot in the real world from the point cloud?
Yeah, so just by using, you have a URDF plus mesh of the robot, and you can just subtract that directly from the input.
Okay, so it looks like sometimes the prediction of direction for execution is not perfectly accurate, but it looks like the compliance of the robot tip is playing some role to make sure it's not doing crazy stops. Do you think variable impedance control can play a role in the future work of this direction?
Absolutely. I mean, that's kind of how we might be able individually as humans to respond to these doors. Like, you think a door is moving in a certain way, you feel it pulling against you. You could use, some sort of impedance control on a robot to have the same kind of behavior. But implicitly, like if you just pull slightly off the axis when you're opening the door, it'll project, like the constraints of the object project your force into the direction that it's going to move.
Thank you.
Yeah.
Hi, I have a question regarding the real-world experiment. It seems like when you are manipulating those real-world objects with relevant joints, sometimes the object itself moves. Is it because of the predicted flow is not accurate enough, or some other reason?
So the accuracy of the flow is pretty high. I would say it's more on the control that we implemented to do this motion planning in the system. So there's little errors in moving the objects. Say you move it 10 centimeters, the object itself is actually going to flow through a small arc, but we're doing this kind of small linear approximation of the arc. If we really crank down the fine-grained control of the simulation, of the actions that you apply in the real world, I think it would result in less motion.
Okay, thank you.
Hello. Great paper. Thank you so much for presenting. How does this model handle ambiguity? Like you can have a half-open door that can both open or close.
So it's kind of predicting almost like a basis for the motion of that point. So you could have kind of a separate component which you add on top of this representation which tells you whether you want to open in the positive or negative direction. By convention, all of the vectors get predicted in the opening direction. It turns out that the data set is very consistent in this labeling. So you can just kind of reverse the flow to give a closing sort of direction.
Thank you.
And last question.
Thanks. Great presentation. Does it do the articulation with a combination of motions, for example, prismatic followed by revolute and so on?
Sorry, I couldn't hear the first part of the question.
Does it predict the articulation with a combination of motions?
Oh, I see. So you're saying like you have a series of kinematic elements.
Correct. Yes.
So in this work, we don't really investigate that. We're kind of doing like a fixed body that has a single degree of freedom afterwards.
Got it.
But I kind of addressed this a little bit earlier. There's no reason that you can't estimate the instantaneous velocity of a multi-chain link. It's just going to be a substantially harder task to do.
Thank you.
All right, let's thank our speaker again. Okay, next up we have Dhruv Shah presenting ViKiNG, vision-based kilometer-scale navigation with geographic hints.
Second. Just give me one more second. I think my speaker notes are not.
Okay, slight change of plans. If you're willing, we'd like to swap the order of the next two. Okay, so let me introduce the speaker. Once I get your thing up here. A slight change of plans. Right now we're going to have Zhenjia Zhu present Dexterity, Deformable Manipulation Can Be a Breeze.
Okay, thanks for the introduction. Okay, hi, I'm Zhenjia. I'm from Columbia University. Today I will introduce Dexterity, a new way of robot manipulation using airflow. When we talk about robot manipulation, it's often all about contact, such as how to model or generate right contact in order to interact with this object. However, many common objects in our daily life are either inconvenient or even impossible to manipulate with contact. For example, it's inconvenient to pick up leaves one by one, and it's impossible to inflate glass with our hands. But they can be effectively manipulated using air. So in this work, we want to enable robotic dexterity with air. So we call it DextAIRity, with an L inside the name. We study it in the context of deformable object manipulation, such as unfolding a crumpled cloth or opening a deformable bag. Both of them are very challenging for contact-based manipulation, but they can be nicely solved with dexterity. So why do we want to use air for manipulation? Here are a few advantages. First, air enables the robot to apply a dense force field. For example, we can extinguish all these candles with only one blow. In contrast, contact-based manipulation can only apply force through sparse contact, which is often not efficient for underacted objects like cloth. Second, air-based manipulation allows the system to reach objects beyond its kinematic reach range, such as leaf blowing in distance. And finally, since air is much safer to move at high speed, it can operate safely around people. To enable these advantages, here is our system design of dexterity. It consists of 3 UR5 arms. 2 are with parallel jaw grippers, and 1 with an air pump. Since we do not require high-speed movements, these robots could also be replaced with other slower and cheaper types. Visual observations are captured from a top-down camera. Here we can see none of these robots could cover the entire workspace or even the surface of a fully unfolded cloth. Therefore, long-range interactions by airflow is a natural fit for this challenging task. We take a learning-based approach to this problem. First, the system infers where to grasp on the cloth. 2 robot arms then lift and stretch it in the middle of the workspace. And then the third arm executes the blowing action. Now let's take a close look at this policy. The network infers a score for each action candidate, indicating the close coverage prediction. The action with the maximum score will be selected for execution. The observation is then input to the policy to infer the next action. With this closed-loop policy, the action could be adjusted in time according to visual feedback. The policy is trained with NVIDIA Flex simulator, where the airflow is simulated as a stream of invisible particles. Here, we compare with 2 popular methods for cloth unfolding. Quasi-static action, like pick and place, is not efficient and requires many interactions to achieve the goal. Dynamic actions, like fling, is able to efficiently unfold the cloth when it is relatively small, such as this shirt. Then, how about our dexterity? Here, we can see dexterity is able to unfold this shirt with only 2 interactions. And there is no need for high-speed robot movements. Here's a larger cloth which can no longer be handled by Flowbot. Even with the maximum fling speed, the cloth can only be unfolded in half. Therefore, better robots with higher speed are required, which is very expensive and dangerous around people. Will Dexterity face the same issue? The answer is no. With the help of active airflow, Dexterity has no trouble of unfolding this super large cloth. Here are more results in real world. We found our approach shows strong generalization ability. While the policy was only trained with rectangular cloths in simulation, it can generalize well to different shaped garments, such as shirts and dresses, from different crumpled states in real world. Dexterity can also be applied to other tasks, such as bag opening. Here, the goal is to open a deformable bag and maintain its open state so that we can put other objects into the bag. Without airflow, the bag opening is often too small, making it really hard to put objects into the bag. But when the bag is opened by air, the placing task is much simpler. Here we can see we can even use inaccurate tossing actions to put objects into it. Here is our system set up for the bag opening task. We assume the bag has already been grasped by 2 robot arms. And the third arm with an air pump executes the blowing action. The policy infers a score for each angle, selects the best one for execution, and adjusts continuously according to visual feedback. Since Flex is not able to simulate accurate air dynamics, such as Bernoulli effect, which is very important to this task. So our policy is trained on real-world data, and the supervision is whether the bag is open or not, which can be automatically labeled from a side view image. We found this task is very challenging for contact-based manipulation. If we only have 2 contact points, there is not much we can do. Even with dynamic actions, like shaking, we cannot open the bag. However, from this video, we can see using air makes this task much easier. Here, we also compare with a heuristic-based policy to show the closed-loop adjustment is necessary. Here is another example with a large plastic bag. In this case, Dexterity opens the bag with only 1 trial. In our experiment, we found the policy trained using only 1 bag is able to generalize well to different bags and random grasp poses. We also observed that our policy learned some interesting strategies. For example, it tends to aim slightly above the bag opening to leverage the Bernoulli effect. To summarize, in this work, we show that air can be used to simplify the many complex manipulation tasks, since it allows the robot to apply a dense force field, expand its reach range, and provide safe, high-speed interactions. With this work, we hope to inspire more innovative ways to incorporate air in robot manipulation. More videos of our system can be found on this web page. There, you can also find the code for both simulation and the real-world experiment. Finally, we will have a live demo in our lab on this Thursday. Yeah. Please come and check it out. Thank you.
All right, questions?
Sorry, fascinating work. So
Okay.
I just have a quick question regarding the generalizability of the system to air blower with different nozzles. For example, for a leaf blower, you can change the nozzle to change the size of the airflow. So have you guys tested that aspect of the system? Thank you.
Yes, in our simulation, we changed the nozzles. Since the air pump we bought in Amazon has 2 extra nozzles, and in our experiment we use the medium one, but we also try the large one. So as long as the airflow is is strong enough, it can generalize to different nozzles. Yeah, so it cannot be too small.
Hi, so manipulation via airflow seems like a really exciting concept, and I found this talk pretty interesting. And I want to ask a question about this concept. So you talked about how with airflow you can apply a force very broadly over a space.
Yeah.
Now, a lot of environments have small objects, light objects like cards and stuff like that, and I come from a aerial robotics community where that can be bad for us because they get moved around and sucked into robots, and that happened during the Subterranean Challenge competition recently. So I want to ask, how do you deal with things like that, and have you started thinking about challenges and limitations of manipulation via airflow?
So your question is how to handle the small object, right?
Yes, yes.
Yes, that's one of our potential limitations. Since the advantage of airflow is to apply a dense force field, but it can also be disadvantage since we cannot have a very precise control of the airflow. But back to the previous question, if we change to a very small nozzle, I think we can still to manipulate some very small objects. But the 2 tasks I show here, like the cloth unfolding and the bag opening, so it's not a small object manipulation.
Thanks a bunch.
All right. Unfortunately, we do have to end the questions a bit early because we have to stay on schedule. So let's thank the speaker again.
Oh, thank you.
All right, so we're back with our last speaker, Dhruv Shah, presenting ViKiNG vision-based kilometer-scale navigation with geographic hints.
Okay, sorry about the goof up earlier. Hello everyone, excited to be here in person. I'm Dhruv, and I'll be presenting this paper on vision-based kilometer-scale navigation with geographic hints. This is joint work with Sergey Levin at UC Berkeley. Let's say you have a small mobile robot tasked with doing last-mile deliveries in a neighborhood like the Columbia campus. Given some high-level information about the goal, such as this picture of Meunier's sculpture right outside the engineering building and its address, the robot must navigate a challenging environment in search of the goal. Without prior access to the environment, the robot must make informed decisions to maximally explore it with the goal information. Current learning-based methods for goal reaching in novel environments fall under one of 2 camps. The first camp relies largely on training from simulated data, often on the order of 1 billion frames. Such methods have shown great promise in solving long-horizon navigation problems by utilizing multimodal information, such as floor plans, but they often require access to a simulation replica of the deployment environment, which can be prohibitively expensive, if not impossible for complex open-world environments. The second camp alleviates some of these challenges by learning directly from data collected in the real world. These systems can learn directly from small amounts of offline data and generalize to visually similar environments. However, these methods have not been shown to use multimodal information to guide the exploration in novel environments, and hence tend to be impractical to deploy in large-scale settings. To extend the capabilities of these systems to more, let's say, city-scale environments, let's take a page from the book of the best embodied navigation agents we know of. When humans navigate new environments, such as when hiking outdoors, we make use of both geographic knowledge obtained from trail maps and learned patterns from their past experience. However, in contrast to geometric approaches of using a map like SLAM, humans don't require the maps to be accurate or metric. A person can navigate a hiking trail or a college campus just fine using a road map on their phones that roughly indicates the streets and houses. In fact, that's exactly how a lot of you got to the conference today. The RSS organizers shared directions in the form of a Google Maps view. This is actually yesterday. And safe to say that people are pretty good at using such maps to find their way around new environments. Can we get a robot to do the same? In this work, we study how vision-based navigation systems can utilize geographic site information to guide their exploration in new environments. Our goal is to devise learning-enabled methods that make use of this information as hints, much like you and I would when dropped in a new environment. This information may be outdated or invalid, for instance, with parked cars or trucks that don't show up on overhead maps. And a good system must be able to deal with such situations. Before we begin, let's look at the search problem we're discussing here. Notably, when I say search, I don't refer to a purely computational graph search problem. Each step in our search problem involves a robot driving to a sub-goal and updating the graph. The common set of graph search algorithms often make some limiting assumptions. First, it's common to visit an arbitrary fringe node from the current node. And second, these algorithms assume a set of pre-specified neighbors in the graph and their corresponding edge weights before you actually visit them. In contrast, as cool as it would be, robots cannot teleport, and visiting a node often incurs a driving cost that needs to be accounted for. And second, the real world doesn't specify feasible neighbors. The robot needs to identify and calculate what neighbors are good for it before it actually visits them. To solve this, we make two key changes to the search problem. First, we use a latent variable model to represent a distribution of subgoals that is reachable from the robot's current location. This allows us to sample feasible neighbors and also predict the estimated cost to reach them. We use this estimated cost, along with a novel goal-directed heuristic, for planning downstream. This encourages the robot to explore both locally as well as globally towards the goal. A local image-based controller, trained on prior data from other environments, reasons about navigation affordances directly from images. It also provides proposals to the planner about which nearby landmarks are likely to be reachable by a sampling process. Meanwhile, an A*-like high-level planner selects candidate waypoints in order to reach a faraway goal. This incorporates the geographic site information as a planning heuristic. This site information is processed using a learned neural network trained with a contrastive objective. And the computed graph is executed physically on a robot in a novel environment. Oops. The latent goal model is an important part of our method. Our context condition model is trained to predict short-range temporal distances to the goal, as well as the best first action towards it using a variational information bottleneck, which takes the form of a compression objective. This objective is robust to task irrelevant features in the observations and can learn a robust prior over reachable goals. Notably, during deployment, this allows us to sample a latent subgoal from the learned prior and decode it into corresponding feasible subgoals or neighbors that the robot can navigate to from the current location. Now that we've talked about how we generate candidate neighbors, we need a mechanism to bias the search problem towards the goal. The simplest thing to do here would be to use GPS to encourage picking the subgoal that is closest to the goal in an L2 sense. In this case, the scheme would pick the subgoal that's on the right. But what if we do have some more context about the environment? Given an overhead satellite images context, it seems that the right dot, despite being closer in an L2 sense, might involve the robot trying to jump fences, and the left dot would instead be closer to the goal in a semantic sense. How do we capture the semantic notion of distance as a planning heuristic? To obtain such a heuristic, we train a data-driven estimator for the probability P that a given waypoint W lies on a valid path to the goal G. Using the same training data as the other models, we learn P with a contrastive objective, which can be seen as a binary classification problem between a set of positives and negatives. Intuitively, given a trajectory in cyan, we sample points along the trajectory and label them as positives, and we sample a bunch of other points not on the trajectory as negatives, and train a neural network to learn a desired estimator that contrasts these two sets. We can use a weighted complement of this estimator to serve as a planning heuristic in our algorithm, which gives us a cost. Okay, which gives us a cost for the candidate subgoal that captures semantic notions of traversability. Putting it all together, the complete algorithm looks remarkably similar to A*, and I won't step into the details here, with a notable exception of the robot physically driving to the computed waypoint. the sampling process, which is used to discover neighboring subgoals, and the contrast probability estimate, which is used as a goal-directed heuristic when computing costs at each time step. It's important to note that these overhead hints are only used as a planning heuristic, while the local control is still purely vision-based. So even when the hints are off, the robot can continue staying safe and explore the environment using its egocentric observations. All learned models discussed here are trained on an offline data set of trajectories that look something like this, collected in a diverse variety of environments, including city sidewalks, hiking trails, parks, and so on. Notably, ViKiNG never sees trajectories longer than 80 meters, but can leverage the learned heuristic to reach goals over a kilometer away. When deployed in a new environment, like this example, we have a goal specified by an image at the top right and on the GPS at the bottom right, using the satellite image as hints. The robot uses its egocentric observations and navigates through complex environments, including following roads, cutting across grass, often going through trees when the satellite hints are actually not valid anymore under the canopy, and eventually reaching the goal. In one instance, the robot drives into a cul-de-sac, and uses its graph to backtrack around and then find the goal. This trajectory is about 1.5 kilometers with me running behind the robot. It looks janky because it's about 20 minutes long, and I'm sped it up for the talk. In this experiment, using a schematic roadmap instead of a satellite image, as you can see on the bottom right, we see similar behavior where the robot is able to use the learned heuristic to drive towards the goal. Interestingly, we see that using a schematic roadmap instead of a satellite image encourages the robot to navigate on marked roads instead of cutting across grassy fields like we saw in the last experiment. In fact, this emergent preference of following roads is consistently observed across multiple environments. This is another example with the same starting goal location where only the hints differ. And ViKiNG can extract better correlations from feature-rich satellite images, while the roadmap induces just following paved roads. I have a lot more videos of our experiments, ablations, and quantitative analysis on the project page that I'd like to show, but in the interest of time, I'm going to wrap my talk here. Our key insight is that effectively leveraging a small amount of geographic knowledge in the form of hints can provide strong regularities that enables robots to navigate to distant goals. We find that incorporating these hints as goal-directed heuristics for planning enables emergent preferences such as following roads or staying on trails in parks, which are induced by the nature of these hints. Additionally, ViKiNG only uses them for biasing the high-level search, in contrast to geometric methods that use these hints more religiously. The algorithm is robust to imperfect hints in the map. And lastly, while we've only demonstrated the system for satellite images and schematic roadmaps, the contrastive objective and the framework we described is fairly general and can be adapted to support more interesting modalities, such as hand-drawn paper maps or even textual instructions, which would be a lot more user-friendly. In fact, this is something we've been exploring in our recent research on enabling embodied instruction following agents. Our system can parse free-form textual instructions into a series of landmarks and ground them in the robot's observations using pre-trained models like GPT and CLIP. This allows the robot to accept fine-grained instructions from the user and execute them on a physical robot without requiring any online fine-tuning, paired language annotations, or simulation-based training. Thanks for your time. I'll just leave some videos playing in the background while we take questions.
Okay. We have time for one short question. Really? Okay, well, I guess I can ask my question. So when you try to compare to a baseline for this kind of work, I know you can't directly compare to A-star planning, without images. How do you actually formulate a reasonable baseline to compare to?
So I think one very nice way to set up some baselines is to try ablating the different components that we discussed. So you can try ablating just the physical search part of it, which is something we do in the paper, and you can have A-star, but then the other parts are your learned parts. Something else you can do is remove the hints and look at the rest of the things just to see how important different parts of the system are. And that is something we have extensively in the paper, and maybe I can share more in the poster as well.
Okay, great. Thank you. Let's thank our speaker again.